Titan, Saturn's largest moon, is the only moon in the solar system with a dense, planet-like atmosphere. About 65% of its surface is covered in vast plains. But what makes Titan truly extraordinary is its methane cycle. This interplay between atmosphere, surface, and interior keeps Titan geologically restless across billions of years. That golden orange color is not pigment, it is chemistry. Ultraviolet light converts methane into complex organic molecules called tholins, forming a persistent photochemical smog high above the surface. Surface pressure here is about 1.5 atmospheres, half again as thick as Earth's at sea level, making it the densest atmosphere of any moon in the solar system. These are not silica grains, but particles of solid organic compounds, swept west to east by seasonal winds into ridges stretching hundreds of kilometers. Molecules forged in the upper haze layers eventually settle and accumulate into sand-like sediment on the ground below. Near the poles, the landscape shifts dramatically. Liquid methane and ethane pool into lakes and seas, with the northern hemisphere hosting the largest of them. A surface temperature of around -179 degrees Celsius keeps water ice as rigid as granite, structurally solid. Ligeia Mare, the second largest sea, is nearly pure liquid methane. Vast and dark, it mirrors the sky above, just as an ocean would on Earth. For decades after the Voyager flybys of 1980 and 1981, Titan's surface stayed completely hidden. Its thick smog defeated visible light cameras entirely. Everything changed with Cassini, which arrived at Saturn in 2004. Cassini's synthetic aperture radar punched through the haze and mapped terrain in extraordinary detail, while the Huygens probe parachuted to the surface in January 2005, returning the first ground-level images from the outer solar system. Titan's atmosphere is 65 kilometers deep. Darker patches across the equatorial plains reflect a higher concentration of organic sediment, raining down from the smog layer and accumulating over millions of years. Radar imagery transforms our view of Titan entirely. What looks like a featureless orange ball through a telescope becomes a world of dunes, seas, mountains, and intricate plateaus, detail invisible to human eyes, revealed only when you observe at the right wavelength with the right instrument. Ridge and valley patterns across the highlands record both tectonic stress within the crust and centuries of erosion by methane rainfall cutting steadily downward. Labyrinth terrain is one of Titan's most striking features, found predominantly near the poles. Scientists think they form through erosion and dissolution, where organic material dissolves in hydrocarbon rain rather than limestone dissolving in water. Each labyrinth plateau is riddled with closed valleys and rectangular drainage networks, suggesting strong structural control over where channels cut. Their bulk composition is primarily organic, with traces of water ice exposed where erosion has bitten deepest into the crust. Cassini's radar and infrared instruments together demonstrate the power of remote sensing, mapping a world hidden behind an impenetrable atmospheric curtain from 1.4 billion kilometers away. From a distance, its apparent featurelessness extends to enormous altitude, scattering all visible light before it reaches the ground. Only by switching to radar or infrared does the true landscape emerge. Titan in full view, a bright polar cap of exposed water ice, giving way to dark equatorial dune belts, a world carved by weather operating on alien chemistry. Grayscale radar passes highlight differences in surface roughness and composition that color imagery cannot capture. A dark linear feature might be a methane-flooded channel, a tectonic trough, or a region where fine sediment has smothered older terrain. Each interpretation carries different implications for geological history. Distinguishing between them requires combining radar backscatter data with infrared spectra and topographic measurements, precisely the kind of multi-instrument analysis that made Cassini so scientifically productive across its 13-year mission at Saturn. Saturn's gravity locks Titan into a near-circular, prograde orbit, keeping one hemisphere permanently facing the planet-a-tidal relationship that also flexes Titan's interior and generates internal heat. Saturn's golden color comes from ammonia crystals in its upper cloud deck, while methane deeper in the atmosphere absorbs red light and shifts its tint toward yellow. Dutch astronomer Christian Huygens discovered Titan in 1655. For 3 centuries, its actual surface remained a complete mystery, hidden behind smog no telescope could penetrate. As Cassini drew closer, Titan resolved from a hazy blob into a detailed world 5,150 kilometers across, slightly larger than the planet Mercury. Titan's entire geological engine runs on carbon chemistry, driven by a hydrological cycle where methane, not water, is the working fluid shaping the landscape. Seasonal temperature shifts drive methane evaporation and condensation between hemispheres, generating cloud systems and methane storms, whose signatures Cassini tracked throughout its entire 13-year mission. Thermal maps reveal localized warm patches, potentially marking cryovolcanic sites, places where a water ammonia slurry erupts from the interior. NASA's Dragonfly rotorcraft, launching in 2026, will explore the surface directly,